Welcome back, everybody, to the Applied Imperative podcast.
This episode, we're going to be going a little bit deeper into a topic that some of you may know and some of you may not have heard of, and it's called Model-Based Systems Engineering, MBSE. We're very lucky to have a really great person here to talk to us about this, somebody that spent a lot of his career thinking about MBSE, helping guide the way that MBSE is deployed and even the rules based around it. And he's had a great career with a lot of experience in MBSE. So I'm looking forward to getting into that with him. That person is Mark Sampson. And Mark, I'm going to hand it over to you.
Well, thanks. I'm getting a big head here. Sorry, Dale. Anyway, well, it'll probably be appropriate to start there. So I graduated out of BYU with a computer engineering degree, and I got hired to go to work out of college at Texas Instruments, and they put me to work in doing automation for electrical, a circuit board, and a chip, and factory automation kinds of things. While I was there, I learned a lot of lessons really quickly. I learned that my beautiful electrical designs got messed up by other people in other domains, like, for example, purchasing. I ended up on a Tiger team. That's a team that's a quick reaction team. The team consisted of a variety of disciplines: chemistry, reliability, safety, you name it. And so what we found out in a chipset factory, these are the chipsets going into cell phones, ended up failing at 90 days. One of the problems with electrical, chips is that you don't find out you've got a problem until the yield rates start going down. And that's where we were at. Anyway, we found out, to make a long story short, as we started chasing the problem, that boron was showing up in the chipsets for some reason, and that boron corroded over 90 days, causing the chips to fail over 90 days. And so we went looking for where boron was coming from. It occurs naturally in the soil there in Texas. And we had filtering systems which takes the boron out of the system, out of the clean room. And for some reason, boron was showing up. And so we went looking. The problem we found, this is always interesting, was that the filters that were supposed to be taking boron out of the clean room weren't being changed as often as they should have been changed. They should have been changed about every, 2 weeks or so. But for some reason, the purchasing agents decided that they could outsource maintenance of those filters to another company. And so that company was changing them out. And of course, what they did is they came back with another assignment that said, hey, let's see if we can reduce our cost, right, for our suppliers. And they said, if we didn't have to change those filters every 2 weeks, we could reduce your cost. So they went down to every 90 days. And so the result was that we saw our yield rates going down over 90-day periods, and then they'd come back up. And that's what we did. And of course, they made this decision. The purchasing people made this decision without understanding the implications of what was going on. I can look at Dale here, and I know he's thinking in the back of his head, this kind of sounds familiar in the aerospace business, right? And so I had access to some forensic accountants, and one of the old timers on the team said, this sounds kind of familiar, this problem. And they went looking back. We had the forensic accountants go back, and they went and they found the same problem that had occurred some 3 years earlier in a different place, a different situation. And so that made us wonder about, well, how often do these problems once solved take to come back, was the question we were starting to ask ourselves. And we found out, in our case, it was about less than 3 years. So we found these problems, of course, are repeating. And the reason they're repeating is because these problems are made by decisions on isolation in silos, And so they're making those decisions without understanding the total implications, the cross implications of that. And so I said, I could use a systems engineering degree, and I got a graduate degree at Southern Cal. And that's when we realized that we could do something in automation for systems engineering. Yeah. Essentially, we created a computer-aided tool for systems engineering, which allowed us to understand the relationships of where things go, that when we had one of these problems, we could follow it and prevent us from repeating these problems over and over again. It's just not electronics has this problem. Automotive, aerospace, everybody has these problems, right? So then we finished that computer-aided systems engineering environment. It's known as SLATE, System Level Automation Tool for Engineers. And we realized we could probably take that to the outside world and make a go at it. And so TI let us go with that technology. We started our own little company called TD Technologies. There's some argument about what TD meant. Top down was what our original intent was, but it was already taken. So it's Top Dog Technologies is what we decided it was. 12 of us that started our own company, and we survived the the 4 to 5 years, and this is where you start to get tired trying to keep everything moving. We put ourselves out for being an acquisition. We got acquired by SDRC. Some of you might remember that. And then SDRC a year or two later got acquired by EDS, and EDS a couple years later sold us off to UGS, which then got acquired by Siemens. And so that's how I ended up with 30 years of experience, because I took it all with me. I know I'm not that old. So anyway, that's kind of a really fast forward of what it was. And then recently I took retirement because Siemens says they gave me a way out. And so I retired here about a year ago now. So that's kind of a fast talk of my career a little bit.
Yeah, that's great. And you couldn't relax enough in retirement. You decided you needed something to keep you busy. So now you're with Applied CAX, right?
Yes, I am. It's been really interesting.
That's great. We're really lucky to have you. So great. Thanks for that history. Obviously, deep systems background. And I know you've got some great examples to share as we go through this. Can you kind of turn that into what model-based systems engineering is? Because it's a different way of looking at a problem, right? You mentioned before silos and making sure all the decision makers are connected. How does MBSE fit into that, and why is it different?
So model-based systems engineering, when we first started having these problems with we recognized that it was a systems problem. And what I mean by systems, other domains, it's a balancing act between all these different electrical, mechanical, software, manufacturing. We're really pretty good at living and working within our silos. We're really good. I think the quote from IEEE at the time when we were at TI was that 90% of our chips work as designed, 50% of them fail when we plug them in. And right. You know, you've got these components that are optimized to do exactly what they're supposed to do, but when you plug them in, they have interactions with other things that end up causing this integration problems. In the past, everybody was talking about how the automation of generating specifications, that's what their orientation was. Just like many of the other domains. Remember, you can probably think back mechanical, aerospace engineering. Dale, I don't know if you're old enough or not to remember the drafting tables and tape on Mylar, those kinds of things. And essentially what it was all about was you're trying to describe what it is you were trying to accomplish, and you would build a set of specifications, high-level specs, that can be handed to the electrical people, the mechanical people, so forth and so on, and say, this is what we want you to do. And you're trying to describe all this with text. And I guess in the olden days, I can look out my window here and see a 66 Chevy, which I'm working on trying to restore. But there's hardly any electrical. There's a light switch and an ignition switch. That's it, okay? And this idea is, in the olden days, we could have probably got away with that, because we could walk down the hall and say, hey, the electrical guy, there was probably 2 of them on my program, right? And I could, to make sure they understood what I was trying to accomplish. But nowadays, with millions of lines of code, how many ECUs do you have in your typical airplane today? I can't even imagine. In the cars, my wife's car has some 200 of them, and how many hundreds of millions of lines of code are running in that thing? The point being is in the olden days, they were busy trying to describe what it is you want to do with text, and that's how it's always been. But text isn't scaling anymore, and so we're talking about moving to models, just like everybody else moved to model. Electrical guys describe things with models, mechanical people, everybody's now doing that. Systems engineering need to go through that same transition or transformation. There's this recognition that we have to move to models. We can no longer be a document-based kind of practice. It has to be a model-based practice, and that's where they're moving to. Okay. Hopefully that answered your question, Dale. The question, though, is how is it that we move to models? And then there's all kinds of interesting problems going along with that. How do you exchange information of a systems model that works with an electrical model, and so forth and so on? That's where all the problems come in. And so MBSE, that's what we're trying to accomplish is make systems engineering a model-based practice, just like electrical engineering and just like mechanical engineering. Now, I'm looking here at Dale. I can't imagine building an airplane mechanically or aero without a set of models. And it's not like we call it model-based mechanical engineering anymore, right? It's not like we do that. But, and hopefully systems engineering will reach that point. It'll just be system engineering, and you won't call it model-based. It'll just be, if you're going to do system engineering, you're going to do it with models. That's where we're trying to get ourselves to. Yeah, no, that's great. Thanks, Mike. Let me just pause us there, because I have a good example of what you're talking about, right? With this level of complexity and sophistication and integration, right, between systems. There was a program I was working on. I was in flight test, and we had
a situation where there was an error code that was being thrown out, and it was to do with the landing gear and weight on wheels. When the aircraft touches down and you get weight on wheels, a number of things happen, right? The spoilers pop up, the brakes go on, all sorts of different algorithms are kicking in, controlling different systems. But this error code took a long time to trace, and it ended up that the water waste system on the aircraft was a part of this logic, because everything was so well controlled and something was happening in the water waste system as you got this weight on wheels signal, and it was throwing up some spurious message somewhere else. So it shows just how massively integrated all of these systems that traditionally were, standalone kind of federated systems maybe on their own, and now it's all, everything's speaking to each other. And to your point, with that comes an exponential growth in software lines of code and all that sort of stuff. And if I was to summarize what you just said, it used to be very paper-based, siloed, mechanical would hand something off to electrical, they'd hand it off to software, we'd go around the loop. And then we realized at some point we had a problem because somebody had changed something. The model-based systems engineering approach, it's kind of in the name, it's model-based, right? So everybody's going to iterate around the model. The model is in the center, the system model, the architecture, the schematic, the model itself. And all those disciplines are constantly interacting with that model, and it's updating real time, and everybody can see all of the changes that are going on together, right? And then you can tie the requirements in, and if requirements are being met, or if you're going to break a requirement that somebody's interested in, and keeping everybody in the loop of that. Is that a fair summary at 30,000 feet?
It is a fair assessment. The example that you gave reminded me of an experience that I had with talking to one engineer. He said it took him forever to find the problem that they were dealing with in some integration problem. And they finally got to the software guys, and they said, weight on wheels. What do you mean? Weight off wheels. You know what you mean? Weight off wheel? You can imagine what that did.